Hello everyone, welcome to another seminar of the Astronomy Department cycle of seminars. Many thanks for joining us today in Google Meet or through our YouTube channel. And we are very pleased to have Dr. Terese Hansen today presenting her work. Many thanks, Terese, for your presence here. And Terese had her PhD at Heidelberg University, and then she became a postdoc research associate at the observatories of the Carnegie Institute for Science in Pasadena. And currently, she's also a postdoc research associate at Texas A&M University. And her research is focused on RProcess enhanced stars, near-field cosmology, and galactic archaeology. And today, Terese is going to talk about the past, the present, and the future of RProcess enhanced stars. But before, I will ask everyone, please turn off your cameras and your microphones during the talk. If you have a question, raise your hand here in Google Meet, or you can indicate this that you have a question in the YouTube chat. And the questions will be asked after the presentation, as always. So, Terese, whenever you're ready, you can start.
Okay, thank you very much. Thank you
You're welcome.
For the presentation, and thank you for the invitation to give a talk here. I'm always happy to share my work. And yeah, so as the title says, I'm going to talk about the past, the present, and the future of RProcess enhanced stars. But why do we care about these stars? So let's take a step back. Next slide, please. So the reason why we care about the stars is basically this, and this is the sort of fundament of my research. I look at stars to try and figure out how we create all the elements in the periodic table. So how does this periodic table come about? This table came out a few years ago, which basically shows the different formation sites or the different formation channels for the different elements. So we have the hydrogen and helium from the Big Bang. Then we have all the sort of light alpha and iron peak element that are created during the life and death of various stars. And then we have all the elements that are heavier than iron, which are produced in these so-called neutron capture processes. And so this is what we're going to talk about. Those are the elements that we're interested in today. And this specific version of the periodic table came out after the fantastic event, which you probably all know about, from 2017, where we had two neutron stars emerging. We saw that for the first time, and we saw the light curve from this event which showed the decay of really heavy elements being produced. So we finally had an observational site for these elements. But what I'm hopefully going to convince you today is that that's not the full story. Next slide, please. So just a little bit of basic on the neutron capture. So we have two types of neutron capture processes. We have the S process and the R process. So when you have a neutron capture, you bombard a seed nuclei with neutrons, and that can either happen in a slow fashion, so that the isotope that you create has time to decay if it's unstable before you capture the next isotope, or sorry, the next neutron. Sorry, go back to the previous slide. Before you capture the next neutron. Which leads you to create elements along this valley of stability, and that's the slow neutron capture process, so the S process. But you can also have such a high flux of neutrons that your isotopes do not have time to decay until you essentially turn off the neutron flux, and that is the R process, the rapid neutron capture process. And so each of these processes are responsible for creating roughly half of the isotopes heavier than iron in the periodic table. So the S process we've known pretty well for a while, but the R process is somewhat more debated. Next slide. And as I said before, we had this lovely event happen in 2017. We had a neutron star merger. These objects or these types of events have for very long been suggested to be an site for the heavy element production, R process production. And we also saw the evidence of that in the light curve that we observed from this event. But we also have other proposed sites. One of these is the collapse stars, which are these massive stars that collapse into a black hole, basically. But during that, they have an accretion disk where you can have a very efficient R process going on. Then we have some exotic type of supernova called the jet supernovae, which is basically rapidly rotating stars that when they explode in supernovae, they have these jets that spew material out, and in these jets you can have an RProcess happening. And then normal core collapse supernova has sort of been ruled out from as a main RProcess contributor, but it's very likely that we still have some production of lighter RProcess elements. Next slide, please. Oh, yes. Yeah, so lighter RProcess elements. So we have all these different sites, and what I try to do is try to solve this question with stellar abundances. So this is basically just an overview slide of how stellar abundances or nuclear astrophysics with stellar abundances work. So you have a nucleosynthesis event, for instance, a neutron star merger, that ejects a lot of material into the interstellar medium. Then you form a low mass star out of that enriched interstellar medium that lives on until today. And then I go to a telescope. This one is the 2.7 meter at McDonald Observatory here in Texas. I point that telescope at my star and I get a spectrum of the star. And then from that spectrum, I can measure the abundances of the different elements in the chemical or in the atmosphere of the star. And for instance, I can measure europium, which you see a line of in the bottom spectrum. And since these stars are low mass and unevolved, the chemical composition of them is basically a fingerprint of the elements produced in the nucleosynthesis event. Next slide. So I said I do this with stellar abundance analysis, and I can give an entire talk on that specific subject. But just to sort of remind you of what goes into stellar abundance analysis, is that we need some information about the atom that we're trying to get the abundance for, or the elements. So we need to figure out what transitions there are in the optical wavelength range. Then we need a model for the star. So we need a temperature, we need a gravity, we need a melicity, and we need some sort of discrepancy, some sort of way of describing the turbulent nature of the gas in the star. And then, of course, we need the observed spectrum. And then we put all that through a radiated transfer code. And then we get out what is shown on the right here. So this is the analysis of a thorium line in a Melpor star. So you have the spectrum is the dots in the figure on the right. The synthetic spectrum that we get from our radiated transfer code is the blue line, which should hopefully fit the spectrum measurement. And then we can get an abundance of thorium in this star. And I've also plotted the synthetic spectrum without any thorium, which is the dashed line you see just above the thorium line, sort of to convince you that this feature is actually thorium. And then we get abundances out which we either represent in this bracket notation way, which is relative to the sun, or we use these log epsilon values for the abundances. Okay, next slide. Okay, so I said I would do abundance analysis of stars, but I can't just use any star to do this work, because I want to probe that one event. And if I look at the sun, which is also a low mass star, which will live on for a long time, the chemical composition of the sun is the combination of thousands of supernova events and probably multiple neutron star merger events. So by looking at the sun, I don't really get a clean signature of one event. So I have to go back in time. And you can see that on the right here, that once you go back to sort of the second generation of stars, well, then the gas clouds from which they formed was only enriched by one or maybe two nucleosynthesis events. So the chemical pattern I find in those stars is really the clean signature of those specific events. And if you look at the figure on the left here, you show how the spectrum looks as we go to lower and lower melicity, and you also get fewer and fewer lines, which once makes the analysis easier, but it also means that some of the lines of some of the elements disappear because there's simply just not enough of the element in the star to measure the abundance to show up as a line in the spectrum. So Melpor stars are both really nice to work with because they're a nice clean spectra, but you also get limited with the amount of absorption lines that you can actually look at. Next slide, please. Okay, So what can we actually measure for these neutron capture elements? What are the elements that we can actually get in spectra of stars? And that's showed here. So you'll see this type of plot a lot in this talk. So this is the atomic number of the different elements, and then you have the abundances, the log epsilon abundance on the y-axis. This is the solar RProcess abundance pattern, which is drawn here as a solid line. And then I've just marked out in blue all the elements that have absorption lines in the optical spectrum, which we can get from ground-based observations. And these are the 33 elements, I think, that we can actually, in principle, get abundances for. Then there are some of them, the red ones, where we have to go to space and get, for instance, Hubble Space Telescope spectra to get those abundances. But in principle, we can get a lot of neutron capture abundances to probe the RProcess. So next slide. However, we can't get those in all metal-poor stars, because if the star is not enhanced in these elements, these RProcess elements, then the lines are simply not there. So we have to find these specifically RProcess enhanced stars if we want to be able to measure all of these abundances. And we're very lucky that they actually exist. So this is what you see here is a comparison of two spectra. The red spectrum is from a star that's not enhanced in RProcess elements, and the blue spectrum is from a star that is enhanced in RProcess elements. So you see all these extra lines that show up in the blue spectrum. For instance, the very strong europium line, which we use as an indicator that these stars are RProcess enhanced, but also other elements like lanthanum and dysprosium and stuff like that. Next slide, please. So the first one of these stars to be discovered was this CS22892-052, which you probably know as the Sneeden star, which was discovered all the way back in the 90s. And they measured abundances in this star. This is a very metal-poor star, so it has a metallicity of -3. And so what they discovered, and what everybody else has done since, is that when you plot these abundance measurements, so the absolute abundances, so this is the plot on the left, when you plot the absolute abundances in this star as a function of atomic number, and you sort of scale the solar system RProcess abundance pattern to it, you get a pretty good match in the heavy element regions, so from barium and up to hafnium. So you can see on the right side of that figure on the left that the solid line, which is the solar system RProcess abundance pattern, really match the abundances that they found in this star very well. For the light elements, the strontium, yttrium, and zirconium, on the left-hand side of the figure, the match is not so good. And they obviously also try to see if the S-process was a good fit, but which is a dashed line, and clearly that's not really a good fit. And the figure on the right just shows when they got better data for this star, how this abundance match really is an excellent fit in the region from barium to hafnium, that middle region. It turned out that when they got some of the heaviest elements, the actinides like thorium, that actually did not match this solar system pattern either. And this this analysis and this result sort of continued. Next slide. So after this discovery, the Hamburg Survey for RProcess enhanced stars carried out this search for these extremely RProcess enhanced stars, because they realized that these were really good to probe the RProcess. And so they took snapshot spectra, which is sort of like short, high resolution, but relatively low signal noise spectra of about 250 stars. And they found 8 out of those 250. That's like 3%, which shows this extreme RProcess signature. And as I said before, the europium line is sort of the indicator of this. So we define these by having a europium to iron ratio at this time higher than 1. And what they also found was that all of these stars were actually found at very low metallicity. So most of them had metallicities around -2.8. So from this survey, they found that these highly RProcess enhanced stars, they're really rare, but also they're really metal-poor. So the RProcess has to be operating at the earliest times in our galaxy. And the plots that are shown here are just the abundances of some of the stars that they found in the survey, again matching to the solar system RProcess abundance pattern, where you see that the heavy range from barium and up match the solar system pattern really well. Next slide, please. So in the past, since this first star was discovered and since the survey of the Terese survey of Bachmann et al., some of these stars have sort of popped up in different places because our general pool of melted core stars has grown significantly. And up until about 5 years ago, we knew about 60 of these stars, which are highly enhanced. The ratio has changed a little bit in the definition of these are highly enhanced stars. So we know about 60 that has a europium to iron higher than 0.7. And then we also need them to have a barium to europium ratio less than 0, because we want to have an RProcess signature instead of an S-process signature, and that's sort of the diagnostic of those two. And what I show in this figure is the abundances of 15 of these stars that has 15 or more neutron capture elements measured. And I alluded to this a little bit in the previous slide, or the one before, that we see this pattern, and this pattern sort of seems to be consistent. So all of these are abundances. They're all scaled to europium, and then the solid line is the solar system RProcess abundance pattern again. And you can see in this middle region from barium and roughly up to hafnium, we have this very nice fit to the solar system RProcess abundance pattern, which has now been deemed the universal RProcess pattern, because we seem to find it in every star that we look at, which is enhanced in europium. Hopefully you can see from the figure that the trend that we saw in the first star with the lighter neutron capture elements, so strontium, yttrium, zirconium, that range, the scatter is much larger, and the fit is not quite as great. And also, if we go up to the actinide, thorium, and uranium, you see that they don't actually match so well either. We don't have a lot of thorium and uranium measurements, but those that we have seem to vary. So this is sort of the status of the past in RProcess elements. So next slide, please. So what we've figured out from these 60 stars that we found so far and the explanation of them is that, well, they're found at very low melicity, so the RProcess operates at the earliest time in our galaxy. They have this universal pattern from barium to hafnium. We see a scatter in the light RProcess elements. This has been suggested to be the signature of multiple production channels, but nobody has really sort of figured out which different production channels. And then we see the scatter in the heaviest elements, also the actinides, which leads to a subset of the stars being actinide boosted, and I'll talk about that a little bit later. So what does that? So yeah, next slide. So we had all these different RProcess production sites, and now we have this very consistent pattern in these stars. So why don't we compare and then see which production site can actually produce this pattern? Well, it seems like they all can. So what you see in this slide, on the top left, you have the yields from different neutron star merger models, which are matched to the abundances of this Steven star, so this first RProcess enhanced star that was found. So the black points is the stellar data, and the color points are the yields from different merger models, and you see that there's a really good match. So yeah, the merger models can match the stars. Then on the top right, you have the yields from one of these jet supernovae, and there, if you in at least one of their models, they also match this this universal pattern for the RProcess elements. So you have, again, in this middle region, a very good match to the black dots, which is the data from the Steven star. Then at the bottom, you have the yields from a collapsar model, and here they compare to the solar RProcess abundance pattern in the bottom right plot, and which are the I think magenta points. And again, you see that they can really produce this the solar RProcess pattern quite well. and produce the entire mass range. So the information that we have now is not really enough from the stars. It's not really enough to distinguish between these models. So why is that? Because we have 60 stars. Next slide. So yeah, we have 60 stars, but the caveat lies in what I've bolded out here is that only 15 of them actually have abundances for more than 15 neutron capture elements are derived. So the other, what's that? I can't do head math, but 45 stars have less element abundances derived. Next slide. And that's showed in sort of more statistical figures here. So here I show the number of neutron capture elements. On the plot on the left, I show the number of neutron capture elements derived and the number of stars which had that number derived. So you can see there's a whole bunch of them that only has 5 or maximum 10 element abundances derived. And actually it's like maybe 3 or 4 that seems to have sort of the full elemental abundance pattern that we can gain from these stars derived, so these 30 or more abundances. The figure on the right just shows the magnitude range of these stars, and again with the number of neutron capture element abundances derived from the spectra on the y-axis. And this might allude you a little bit to why that since even though we have 60 stars, the abundance information that we have from these 60 stars is slightly limited because they're really faint, most of them. Next slide. Next slide, please. Oh, yeah. Yeah, so why, I mean, if we have 60 stars, why can't we get all of these abundances? I mean, why can't we get all these blue points that I have in this figure? And well, that's because it's hard. Next slide. So there are elements that are easy to measure, so that show up with really strong, beautiful lines in the spectra. These are like strontium, barium, and europium. So those we can get for a lot of stars. Next slide. But when we come to the sort of the light elements and also the very heavy ones, so like silver and palladium, the lines get weaker. There are fewer lines. They're more in the blue. They start getting blended. The same with the third peak element, like osmium. Next slide. And then there are the the ones that are just downright almost impossible to get abundances for, and those are uranium. For instance, we have one uranium line, and it lies in the wing of this very strong ion line. So on the top here, you see two uranium synthesis of 2 uranium lines in 2 different stars, and you can see there's barely a feature showable in the spectrum. But also an element like lead is really hard because, again, we only have one line and it's blended with carbon most of the time. So it's really hard. We really need high resolution, high signal to noise spectra to get all of these elements. Next slide. Yeah, so we have 60 highly outprocessed stars. That's not a very big sample, so we would like to have more. But we also need these stars to be brighter so that we can actually measure the elements that we want from the stars, so we can actually measure the neutron capture abundances from the stars. And then, I don't know if you noticed, but in the previous slide showing the abundance pattern for the literature sample, there was almost as many references at the bottom as there were stars in the plot, which means that the analysis of these stars is not very homogeneous. So we need to do this in a more homogeneous way so that we can say that subtle differences in the abundances are not due to different analysis methods. Next slide. So that is where the present and the RProcess Alliance comes in. So the RProcess Alliance is a project that was started in 2016 by me and the people listed at the bottom here. And basically with the very ambitious goal to solve the RProcess. And how will we do that? Next slide. Well, we will build a statistical significant sample, a large sample of these RProcess enhanced stars from which we can get a significant amount of abundances and sort of thoroughly map the neutron capture element abundances in these stars. And to do that, we have started a survey targeting bright stars, but also cold stars. So we're sure that we can actually measure these abundances, and metal-poor stars, so that we know that they only probe a few nucleosynthesis events. Next slide. So we pick our targets from large surveys, it's like the RAVE survey. And then Vinny Placco and Tim Beers has done a lot of legwork on this, getting medium resolution spectra of these stars, from which we can get a temperature of the star, and we can get a metallicity of the star. And then we can select them for the higher resolution part of the survey. Next slide. So we can take these pre-selected targets, cold metal-poor targets, right? And then we take it to our favorite 2-meter class telescope. What you see here is the DuPont telescope on the top left, and the McDonald 2.7 meter on the right. These are two of my favorite small telescopes that I've spent a lot of nights on. And then we get these snapshot spectra, as we call them, which are high resolution, so resolution around 25 to 30,000. And also reasonably high signal-to-noise spectra, because we want to be able to find this europium line, which is shown in the spectrum at the bottom, at 4130 angstroms. So the top spectrum is a non-RProcess enhanced stars, and the bottom spectrum is an RProcess enhanced star. So you see this europium line just sort of pops out of you. But we need these high-resolution spectra to find this line. The dysprosium line on the other side of the spectrum snippet, has also turned out to be a very valuable diagnostic of these stars. Next slide. So we've done this for, well, since 2016, so 5 years now. And we've observed about 2,000 stars. And this is the spatial distribution of our targets. The red dots all represent stars that we've observed, as you can see, mostly in the southern hemisphere. And the blue dots represent stars that are still on our target list, and we will get observations for if we can go back to the telescopes. But yeah, we've been pretty efficient in collecting stars in the last 5 years. Next slide. So once we have these stars, we of course want to know if they are RProcess enhanced or not. So we do a abundance analysis of them, and we separate them into 3 different groups. Obviously we look for these highly RProcess enhanced stars, these highly europium enhanced stars, and that's sort of the category that's shown on the bottom here with the blue synthesis. So you have on the right panel, you have this very strong europium line indicating that you have an RProcess enhancement. We also needed to have a higher europium than barium to make sure it's an RProcess. So we also need to measure the barium. And so we select these highly RProcess enhanced stars, which we call R2 stars. And then in the middle, in the green synthesis, you see a similar type enhancement, but just with a lower europium enhancement, basically. So these mildly RProcess enhanced stars, which we call R1 stars. But then one thing we decided in this survey, which hasn't been done before, is also to focus on stars which we call limited R stars. And those are stars that doesn't have a strong enhancement in the heavy element europium, but shows a very strong enhancement in the light element strontium. So basically having a strong enhancement in the light elements compared to the heavy elements, which hopefully will allow us to focus on this this scatter that's seen in the light RProcess abundances. Next slide, please. We've looked at 600 of the 2,000 stars so far, and we've been very successful in finding these different types of stars. So we found 72 highly RProcess enhanced stars. We found lots of the mildly RProcess enhanced stars, and then we found 42 of these limited R stars. And what you see in the plot here on the right is the sort of combined plot from our latest data release paper showing all of these stars. So the europium abundance of all of these stars as a function of metallicity. And this is what prompted this new division at 0.7 in the europium enhancement instead of +1, because there seems to be a difference in the distribution that sort of cuts there. So we now define R2 stars as stars with europium to iron abundance higher than 0.7. And then we have the R1 stars with lower abundances. But what you can see from this plot is that this previous result that all the highly RProcess enhanced stars were found at low metallicity is not really true. We find R2 stars and R1 stars covering our entire metallicity range from -3 and up to almost -1. The limited R stars, however, seem to be clustered around the lowest metallicities in our sample, so there might be some indication to the progenitor there. Yeah, so that's next slide, please. Yeah, so for some of these highly RProcess enhanced stars, our snapshot spectra are not really good enough to completely map the chemical pattern, because these stars just have so many lines, and especially in the blue. So we go out and we get these portrait spectra, which are of 80,000 or higher, which we can get it, and they have signals noise of at least 100 or maybe more down in the blue range. And an example of that shown here. So the bottom plot sort of shows the entire spectral range that we have for this spectrum. And you can see in the blue end, sort of below 4,000, that it's just all lines. I mean, if you didn't know, you might think that it was noise, because there's just so many lines. But when you zoom in, which is shown on the top on one of these areas, you see that it's just because there are such an abundance of neutron capture element lines in the spectrum, in the solid one, compared to the to the one in gray, which is a non-RProcess enhanced star. This star is also somewhat metal rich, so it's not a -3 star. I think it's a -1.5, which also means that there are lots and lots of lines that we need to look at. Next slide. So we've gotten these portrait spectra of a few stars in our sample and analyzed them, and this is the results. So this is the same plots as you've seen earlier. You see the atomic number on the x-axis and the absolute abundances on the y-axis, and then the scaled solar system RProcess abundances as either a solid line or the red line in the top left plot. And again, as we expect, we have this very nice pattern. But what I want to allude you to in this plot and with these results is that we are able to measure thorium in all of these 3 stars. We are able to get uranium in one of the stars. Actually, this is the most uranium-enhanced star that has ever been found. And also, if you look in the lighter end, so the elements around from sort of 30 and up until 45, you see that we can get more elements than just strontium, yttrium, and zirconium. We can actually get molybdenum, ruthenium, silver, palladium, those elements that very few people have measured in other stars. So next slide, please. So just to show you the sort of statistics of it, this is like the figure I showed before with the number of neutron capture elements measured in the different RProcess enhanced stars. And the RPA result has, I mean, in all of our stars that we've looked at in this detailed way, we are able to measure at least 20 or more neutron capture elements. So the promise of this sample is really good, and we'll be able to get very detailed abundance patterns. Okay, so that's this survey has sort of been aimed at the halo, but in my abstract, I said I would talk a little bit about RProcess enhanced stars in other places as well. So next slide, please. So RProcess enhanced stars has not just been discovered in the Milky Way halo, but also in the classical dwarfs. There's, for example, this COS 82 star, which was discovered in the Ursa Minor dwarf royal galaxy. Again, with the abundance matching the solar system RProcess abundance pattern. So those are the red dots here, the COS 2 abundances, and the other 2 blue points are different halo stars. This was actually also the first measurement of an actinide element, so thorium, in a star outside the Milky Way. But we have also discovered RProcess enhanced stars in other galaxies recently. Next slide, please. So we started to discover these RProcess enhanced stars in these ultra-faint dwarf galaxies, which are these really small systems, low luminosity, that are dominated by dark matter, and which contains stellar populations that are metal-poor, old, and has generally seen a very simple chemical enrichment. And you probably all heard about this Reticulum 2 galaxy that was discovered about 5 years ago, where the analysis of 9 stars showed that 7 of them had extreme enhancement in these neutron capture elements. So that's what you see in these 3 plots. You have the strontium on the left, the barium in the middle, and the europium on the right, abundances as function of metallicity. And you have the stellar, or the halo sample in gray dots in the background, and then other ultra-faint dwarf galaxies plotted as the other colored points. And you see, for most other ultra-faint dwarf galaxies, we found these very low neutron capture abundances. But this particular system had a huge enhancement in some of the stars. And the fact that we find this in a closed system can tell us something a little bit more about the progenitor. So at the time that Reticulum 2 was found, we hadn't seen this enhancement in any of the systems, and we observed, or we looked at the chemistry of at least 10, probably more systems. So that told us that this RProcess that creates these this signature is rare. It doesn't happen very often. But also the fact that these stars are so enhanced tells us that it has to be a fairly prolific event. It has to be very efficient in creating these neutron capture elements to be able to enhance the stars to this level. So the environmental, or the fact that we find them in a closed environment where we know the event that happens can give us extra information about what event happened. Next slide. So after Reticulum 2 was discovered, a few other galaxies followed. One of them is Tucana 3, where we also found that the stars had a RProcess enhanced signature, but these stars are sort of mildly RProcess enhanced. So again, you have the strontium, barium, and europium abundances of these stars at functional metallicity. And in the europium plot, you can see that the dashed line there sort of indicates the 0.3 enrichment level. So you can see the stars are just a little bit above that. So they're sort of mildly enhanced, all of them, all of these 5 stars that we looked at in Tucana 3. Now Tucana 3 is a galaxy of similar size as Reticulum 2. So either this RProcess event was less prolific, less efficient, or Tucana 3 has lost some mass. And there's actually observations of tidal streams from this galaxy suggesting that it was more massive in the past. So there's more gas to dilute the RProcess ejecta. Next slide. So the third ultra-faint dwarf galaxy has an RProcess enhancement, this GRU-2 that I analyzed last year. And we were able to do analysis of 3 stars in this galaxy. And one of them show this a little bit enhancement in RProcess elements. So again, the barium, europium, and strontium abundances for the stars in GRU-2 are the black points, and other dwarf galaxies are the color points, and the gray dots are the Milky Way. And you see in this middle plot, we could only get upper limits for europium in 2 of the stars, but in 1 star we could measure europium abundance of about, I don't remember, somewhere about 0.4 dex. And if we look at the barium and strontium, we can see that this star is also enhanced in those elements compared to the other 2. So clearly that 1 star has seen some additional enhancement. So clearly slowly we're building a sample of different levels of enhancement in ultra-faint dwarf galaxy stars, and also different amount of stars that has been, for Tucana 3, it was the entire galaxy, or well, not the entire, but our entire sample that showed this enhancement, whereas in Reticulum 2 and this GRU-2, it's only a subset of the stars that show this enhancement. Okay, next slide. And just to convince you that this is actually RProcess, these are the same plots as I've shown before. The abundances compared to the solar system RProcess abundance pattern. So you have the Reticulum 2 on the top left, Tucana 3 on the top right, and the GRU-2 star on the bottom. The bad thing, not bad thing, but the limited thing about these galaxies is that they're so far away that it's really hard to get abundances for a lot of elements because these stars are really faint. So that limits our ability to explore these galaxies. Okay, next slide. So another place that we started to find RProcess enhanced stars are in streams. And I'm part of the Southern Stellar Stream spectroscopic survey, the S5 survey, where we found this Indus stream, which is indicated on both the plot on the left and the right. I won't go into too much detail because I'm running out of time, I see. So let's just move to the next slide. What we found when we looked at the abundances of this stream is that, which is what you see here, the lilac points are the 7 stars that we could get high-resolution spectra for in the Indus-stream. And one of them, as you see on the bottom left, is highly enhanced in europium and has a barium to europium abundance of less than 0. So it's an RProcess enhanced star. Next slide, please. And we did a very detailed analysis of this star, and that's the result. And again, it's an RProcess enhanced star because it follows this pattern. But it because it's in the Milky Way halo, it's a stream star, we can actually get abundances of a lot of elements because it's closer. But also because it's a stream star, we know that it was born in the dwarf galaxy, so we know it's been accreted to the Milky Way halo system. And therefore, we can use that information similar to the ultrafaint dwarfs to say something about the RProcess enrichment of this system and the RProcess production site once we get a sort of more complete description of the system. Okay, next slide. Right, so that was the past and the present. I'll see if I can talk a little bit about the future in the past last 5 to 10 minutes. So we have these RProcess enhanced stars that are being discovered in dwarf galaxies and streams, and we have this large sample in the Milky Way halo, which will give us a lot of abundances for a very, very large sample of RProcess enhanced stars. And this sample is bright, so all of our stars in the RPA sample would be observed by Gaia, and I'll talk about what that means for the analysis in a second. So what can we actually do once we have this sample? Next slide, please. One of the things that we can look at, and that we've looked at sort of preliminary, is that we can compare the lanthanide fraction in these RProcess enhanced stars with that was observed in the neutron-star merger. So from the neutron-star merger, you had a blue signal and a red signal, which was basically the signal of light neutron capture elements and the signal of heavy neutron capture elements. So they were able to measure ratio between these 2 mass ranges of the RProcess. And similarly, we can do that in the stars. If we look at the figure on the left here, you can take the abundance measurements of the light neutron capture elements and compare those to the abundance measurement of the heavy neutron capture elements, and you can get this lanthanide fraction. And the result is what we have on the right. So the black points show the measurement of lanthanide fraction in the 2017 kilonova from different sources, and they all agree quite well. And then the blue curve shows the sort of general lanthanide fraction if you take all metal poor stars and not just RProcess enhanced, which is a little bit more lanthanide rich than what was seen in the merger, but it's consistent with the errors. But if you take just the RProcess enhanced stars, which is the orange curve, you get a much more lanthanide rich signal than was seen in the 2017 merger. So from looking at the lanthanide fractions of these RProcess enhanced stars, we can say that if neutron-star mergers are to remain as a viable candidate for the production of all RProcess elements in the universe, well, then in the future, we need to see at least 10% of the kilonova that has a very high lanthanide fraction, and much higher than the one that was observed in the 2017 event, to be able to match these RProcess enhanced stars. Next slide. Another thing that we can look at is, I alluded to this a little bit, that we have these stars that have very high abundances in the actinides, so thorium and uranium, but we also have stars that are very low abundances in the actinides. And we don't really understand what causes this or what's the reason for this. So what you see here is the thorium to uranium abundances of stars as a function of metallicity. And because thorium and uranium are radioactive elements, we can use them to determine an age for the star if we know the production ratios, which we clearly don't, because the actinide booster star, so the green symbol in this, the most actinide booster star we know, when we calculate the age for the star, we get a negative age, which you can see on the scale on the right. And the most actinide deficient star we know, this orange dot, which was actually found in reticulum 2, when we calculate the age for that using current production ratios, we get an age that's larger than the age of the universe. So clearly there are some discrepancies here, and we need to learn more about this. Next slide. Yeah, I think I'll skip this, so go to the next one. Please ask a question about this if you want to know. I'd said that all of our stars are bright, which means that they'll be in Gaia, and which means that we can do this dynamical analysis of them, so we can see when they cluster in different dynamical space. So most of these stars that we look at were probably born in dwarf galaxies like Reticulum 2 and Tucana 3, and then accreted onto the galaxy later. And when a galaxy is accreted, the stars obviously keep their chemical signature, but they also keep their dynamical signature. So by looking at the Gaia from data, or data from Gaia, we can pair stars together that has the same dynamical signature, and hence were born in the same dwarf galaxy that was then later on accreted by the Milky Way. And by doing this, we can actually, so this is what's already done in this figure by Ian Roeder for a limited sample of RProcess enhanced stars, and you see this clustering. There are stars that definitely cluster in this action energy space. And by having this knowledge, we can look at different abundance signatures, such as the actinide booster signature, see if that is just a signature of one subsystem, if that was just one weird event in one dwarf galaxy, or if that appears in all of the systems, basically, and we need to have all of the different nuclear synthesis events to account for this signature. So this type of analysis, this chemodynamical tagging, would be very powerful in the future for our 2,000 star sample, where we can put them into different groups and use that to investigate the different signatures of those groups, and thereby also the range of RProcess events or nuclear synthesis types that we need to map these abundances. I think that's it. So next slide. Yes, so this is my summary. I'll leave you with that, and apologize for going a little bit over time, and take any questions. Thank you.
Thank you very much for, it's not a problem. It's fine with the time. Thank you very much for your talk. I will, well, Reynaldo, you can start with your question, then I follow you.
Hi, Terese. Thanks for the talk. I have two questions. In fact, one question. I would like to let me start for the first one. In the beginning, you told us that this analysis involved that you need to assume some model for the atmosphere of the star. Mm-hmm. I would like to know how much uncertainty this introduces, or if it's not significant, if this uncertainty. And another part, if you could explain more about those strings that you showed in slide 38.
Yeah, so the model, there are two parts of that question. So one thing is that the cell parameters that we use to create the model from, so the temperature, the gravity, and the metallicity, the way we determine those obviously introduce, well, not the way, but the uncertainties of those introduce some uncertainty that propagates through to the abundance measurement. The other thing is that the model atmosphere that we use now are what's called one-dimensional plane parallel, and a star is obviously not one-dimensional, it's three-dimensional. So there is likely some offset in the abundances that we derive from these 1D models, and in the future, a full sort of 3D modeling would be nice, but it's very computational heavy, and I hope to do that in collaboration with people at Stockholm University for this sample. But yeah, in terms of the errors, that's sort of why we need to do this in a homogeneous way, because, as I said, in the past, most of the RProcess enhanced stars has been analyzed by one group here and another group there that's sort of taking a couple of stars each. And for instance, if you if your temperature scales are off by, say, 150 Kelvin, that for these cold stars can give significant differences in the abundances that you derive for the elements. And that's not actually a large offset. I sometimes include a slide where I list the different temperatures and cell parameters that they derive for one of these very one of the stars that's been analyzed a lot, like the Steam star, for instance. And the range of what people find from, state-of-the-art analysis, which we all believe is true, it's like more than 200 Kelvin in temperature, for instance. So it's really, it's not so much obviously we want to find accurate stellar parameters, but it's also the homogeneity in it that we need to do it in the same way for all the stars, because then we can say, okay, well, if there's a difference in the abundances, then it's not due to the analysis methods, it's due to the actual star.
Right.
Sorry, the other question was?
If you could explain more about those streams that you showed in slide. Maybe it's one before 37.
Right, so the streams are, so when a dwarf galaxy or a global cluster comes a little bit too close to the Milky Way, it starts to get accreted by the Milky Way. And the stream stage is sort of this first stage where you still have a spatially coherent structure of the stars in the sky, which you can see in those overdensities in the plots on the left. Those are photometric data taken by the by the Dark Energy Survey. And you see those overdensities where it's a lot darker because there's a lot more stars than in the sort of average of the area. And those are simply systems that are slowly being accreted by the Milky Way, but hasn't fully merged into the Milky Way yet.
All right, it happens naturally because of the dynamics of the accretion onto the Milky Way. Mm-hmm. Thank you.
I have a short question related to that. So how you establish that a star is a member of the stream?
So first we detect them in the photometric data, and then the plot on the right, I'm sorry I didn't go too much into detail with this, but the plot on the right shows the fields that the S5 survey has carried out spectroscopic follow-up on. And so by measuring the melicity and the radiolocities of the stars, we can sort of figure out if they match into the same system. And obviously also we use the Gaia dynamical information because for them to be in a stream, they have to be in a spatially defined area altogether. Actually, one of the ways so I said both global clusters and dwarf galaxies come in, and dwarf galaxies make these sort of, well, not puffy, but sort of extended streams on the sky, where global clusters make a more sort of thin stream. So that's one way to get
to the
different.
Okay.
Mm-hmm. Yeah.
Okay, thank you. So Professor Melendez also has a question.
Yes, thank you for the talk. And you mentioned that stars at low metallicities are good because then we can see the effect of just maybe one or a few supernova events. So is there any limiting metallicity that we can say, below metallicity minus 1.5, we have only one or a few events? Is there any limiting metallicity?
That's a hard question. So I guess the answer is no, because it also depends on what environment they were formed in, the stars, right? But for the Milky Way halo stars, for instance, you start to see signatures of the S process contributing to the abundances at about minus 2.5 in melicity. So really, we want to keep it below that. But one of the stars that I showed the full abundance pattern from the RProcess Alliance in one of the last slides is actually a minus 1.5 star, which has this very clean RProcess pattern. I think it's probably a little bit before. It's like before the dwarf galaxies and the streams. So further. That one, yes. Oh, sorry, that one. So the one on the top left here, I think the melicity of that is minus 1.5. And obviously, the abundances match the solar system RProcess abundance pattern really well. So the question is, has there been any S-process contribution to this star in significant? I think if we choose them as having a low barium to europium ratio, so we're sure that it's an R-process, then we can go up to higher melicities like this star. But the problem is that once you get up to, I mean, above -2.5, you do start to get an S-process contribution.
So let's move on with Reinaldo's question. Do you have another question, Reinaldo? Or?
Yes. For me, it was a very... in the introduction, you showed that, for example, events of neutron stars merger give some signature in the enrichment of some elements due to RProcess, right?
Mm-hmm.
Is it possible to, from your observations in the Milky Way, to build some, to make some estimate of the rate of these events independently from other observations, just from these measurements of the abundances?
Yes. So, I mean, if we assume that neutron star mergers are the only place to produce RProcess elements, then obviously we can take the RProcess enhanced stars and say, okay, well, in a neutron star merger, we get roughly this amount of europium out, for instance, and we have this accumulated amount of europium in our stars, so we need this amount of neutron star mergers to have happened. People did that after the 2017 event, and I think the result was that it didn't quite match up. But also, I mean, the neutron star merger rates were very uncertain because we only had one observations, right? And they could only do a statistic on what could or could not have been detected by LIGO, I guess, and gamma ray bursts and stuff like that. So yeah, that's definitely one of the things that once so the combined LIGO-Virgo Karga array will start observing again next year, I think is the plan. And once we get more solid rates on neutron star mergers from that, we can compare that better to the stellar abundances. And that might be a way of saying, okay, neutron star mergers are not enough. We need something else to contribute. Or neutron star mergers are fine. That's also an option.
Thanks. Great.
Okay, we have another question by Professor Rossi.
Thank you. Hi, Terese. It's just to say hi. It has been a long time since we see each other.
Yeah.
So I was very glad when I heard that you accept our invitation to give us such a cool talk.
I hope to come and talk to you in person next time.
No, it was very cool. I mean, it's super updated, something that I personally was looking for. And I guess you know that we are already working on dynamically structures in the galaxy.
Yeah.
And thank you very much for all information. It's so nice to see you, by the way.
Yes, you too, absolutely. I wish I can visit in person next time.
Yeah, sure, next year.
But yes, absolutely.
We hope for that. So take care. It was really a pleasure to see you again. And thank you again.
You're welcome. Thank you for inviting me. That's always good.
Bye-bye.
Bye.
Okay, I will finish with another question I have that is related to the spatial distribution of your sample, the new sample that you have in the galaxy, that you showed what objects you have already been observed, and you know, these that are red and blue points. I was wondering, would you expect some clustering? Because I would expect that where you're looking to these stars, and also you would expect these like streams also, like.
Right.
Would you expect clustering of some sort?
So No, well, I mean, yeah, some of these stars are probably members of streams, but since we don't really use the dynamical information of them yet in the target selection, then we don't really expect any clustering. This is something that we, can do when we have the Gaia information in the future. Then we can say, okay, well, this particular star or these particular stars are members of the stream, so let's go after all the other stars in that stream. But I think the idea about these stars is that most of them are probably fully accreted and fully merged into the Milky Way, and so you just, even though they were still accreted from a dwarf galaxy, they're not spatially connected on the sky anymore because they've
lost the information.
Well, they haven't lost the information, but they've just been completely merged into the Milky Way.
Okay.
So you can still, well, I mean, that's the thing I showed with the last plot, is that you can still pair them together in these action energy spaces with the Gaia data, but they're not found next to each other on the sky because they're fully fully merged into the Milky Way. I'm not sure we have enough stars in the sample to find streams, if there are streams in our sample.
Okay.
We'll probably only have a couple of stars in each stream, and that's not really enough to
because I was going to ask the opposite question, like, would you expect to, from your complete sample, let's say, do the opposite? Like, okay, we found a stream. After you process all the data, say, okay, we found this stream that we didn't know, or something similar.
Yeah, I mean, that is in principle possible. As you said, when you just take a quick look at our spatial distribution, there's no structures that sort of pop out. So I'm not sure that we have enough stars in whatever streams we probably have stars in to recognize them as streams. So yeah.
So more data.
Well, combining data from different sources, really, because I mean, the 2,000 stars is going to be great, and once we get abundances for all of these stars, I mean, I just talked about the Newton capped elements, but obviously we'll also be able to get all the alpha and the light, so anything from lithium and up to the Newton capped elements, right? So this will really be a exquisite sample of abundances. And then we can do all the fun things with Gaia and compare to other observations like the neutron star merger stuff and that kind of thing.
Yes.
So yeah.
Okay, thank you. And there's a question from YouTube, Reinaldo.
Yes.
Okay.
Yes, André Rodrigo da Silva, he's following via YouTube, and he sent the question, have the RPA tried to match those R1/2 stars to the larger merger events like Gaia, Enceladus, Sequoia, or others?
I don't know if we specifically tried to match them to those events. We did there was a paper that came out earlier this year where we did a dynamical analysis of the full sample of published stars that we have, not the full 2,000 sample, but for the stars in all the 4 data release papers. I don't remember if there's any mentioning of stars, but I mean, we have to have stars in those systems, right? I believe there was a paper earlier last year which showed that the Gaia Enceladus had sort of an average enhancement in RProcess elements in general. So very likely we also have stars in that system. But I don't remember any specific matches.
Thanks.
Thank you.
Okay, so let's thanks again. Thank you, Terese. Again, thank you very much for your talk and for your time and for this time of discussion. So we can cut the YouTube now, but we can still be here in the...
And thanks everyone following
yes.
via YouTube.
Yes, thank you very much. Thanks for the invitation, and thank you for listening, everybody.
Bye, Terese. Thank
Bye,
you
Sylvia.
very much again. See you soon.
Yes. See you soon, hopefully.
So,
Hopefully. Bye-bye. Take care.
Richard.